The base of a solid is bounded above by the line y equals x plus 2 and bounded below by the parabola y equals x squared. Cross sections perpendicular to the x-axis are equilateral triangles. Find the volume of the solid. First step is to draw the graph. So we have a line y equals x plus 2 and a parabola y equals x squared. That's not that bad. So, y equals x squared. It's a sketch. It's not exact. It's not symmetric. But anyway, that's y equals x squared. Now, y equals x plus 2 will be a line with a slope of 1 and a y-intercept of 2. The line will intersect the graph twice. Let's find where they intersect at. Let's set them equal to each other. Ship over the x by subtracting it, and the 2 by subtracting it, you'll have x squared minus x minus 2. That'll be equal to 0. Thankfully, that's factorable. It's x minus 2 times x plus 1. So either x is 2 or x is negative 1. Alright, so these are the places where they intersect at. Negative 1 and 2. So our region has a base between these two, bounded above by the line, bounded below by the parabola. This is the base. Now here's what we're going to do. Perpendicular to the x-axis, we're going to have equilateral triangles shooting out of the screen. Okay? And that's going to give us some three-dimensional shape, and our job is to find the volume of that shape. The side of the equilateral triangle goes from the line down to the parabola. Alright, let's find the area of a typical cross-section. So the cross-sections are perpendicular to the x-axis, and they are equilateral triangles. And so I'm going to have this distance from the line down to the parabola basically be the side length of an equilateral triangle. Shooting out of the screen will be an equilateral triangle with each side as long as the orange line here. Well, the formula for the area of an equilateral triangle based on the side length from the formula sheet that you have is root 3 over 4 times the side length squared. So we need to be able to represent the side length. We have a picture of it, but we need it, and it needs to be in terms of x, because our cross sections were perpendicular to the x-axis. This integral is going to be in x. And so, well, how long is that? It's the line minus the parabola. So it's negative x squared plus x plus 2. That's how long it is. That's what we need to square. It's not the easiest thing to do, but I learned this trick from a student. It works out really well. We take the one times the other. Now we could multiply it out. It gets a little messy if you do it that way. There's this tool that you can use where you take the trinomial on the left, write it in the rows, take the trinomial on the right, write it in the columns, and multiply whenever a row and column intersect. So we'll have x to the fourth, because negative x squared and negative x squared multiplied to give you that. Then we'll have negative x cubed. Then we'll have negative 2x squared. We'll have negative x cubed, x squared, and 2x, negative 2x squared, 2x, and 4. What's also nice about this, I mean, it does the 9 multiplications that you need, but it even organizes them. Along diagonals, you'll have the powers to combine. So here it is. Rather quickly, x to the fourth minus 2 of those x cubed minus 3 of those x squares, because we have minus 4 then plus a 1, plus 4 of those x's plus a 4. That's the side length squared. That is going to be what we integrate, right? The volume for cross sections would be to integrate that. So this is the area of our cross section. Step 2 is now done. Root 3 over 4 times that polynomial. Alright, well the third step in the process is just to perform the calculation. So we integrate that from some a to b. Now remember, a was the first place they intersected at was -1, the smaller number, and the other place they intersected at was 2. So from -1 to 2 we have to do this. Alright, so antiderivative, just using the power rule. It's not bad. So we have x to the 5th over 5. Here we'll have x to the 4th over 4, but the 2 will turn the 4 into a 2. Here we have x cubed over 3, so the 3's would cancel. We just get x cubed. We have x squared over 2, so the 4 will turn into a 2. And then finally we get 4x. That's the antiderivative using the power rule in reverse. Fundamental theorem of calculus says you're going to plug a 2 in and plug a -1 in. I like to write it out. It seems a bit tedious, but it helps me to avoid mistakes if I write it out. Physically replace every x with a 2. Physically replace every x with a -1. Be on the lookout for odd powers of a negative. So what's 2 to the 5th? That's 32. What's 2 to the 4? That's 16. Over 2, that's an 8. -8. 2 cubed is another -8. But here we have 2 squared times a 2, which is +8. And then a 4 times a 2, which is a +8. On the other side here, be careful, it's a -1 that's to the 5th, so it's a -1 fifth. Be careful here, it's a -1 that's to the 4th, but then there's a negative on the outside, so that's a -1/2. Wow, this could be trouble here. It's a -1 that's cubed, and then there's a negative on the outside, so it'll be a +1. And then we have a 2 and a -4. Alright, great. All these 8's cancel out. The 2 -8's cancel with the 2 +8's. So you're looking at a 32 over 5. Apply the negative. Be careful, that's where a mistake could happen. Plus the 1 over 5, plus the 1 over 2. Putting all this together, this is a -1, but apply the negative to it, it becomes +1. Let's go ahead and put these two together since they're both already over 5 and call it 33 over 5. And then we know what 1.5 is. That's 3/2. Common denominator is 10. We multiply by 2 here. We multiply by 5 here. So double 33 and get 66. 3 times 5 is 15. That's all over 10. 66 and 15 add up to be 81. Nothing we can do to cancel. So 81 over 10 times that root 3 over 4, which is from the area formula. Putting it together, let's just call it 81 root 3 over 40. And that's your answer. That's the volume of that shape.